Welcome to a lesson on directional derivatives. The goal of this video is to determine directional derivatives of a function of two variables. Let's first review the meaning of partial derivatives. Remember, the first order partial derivative of a function of two variables tells us the slope of the tangent line at a given point in either the positive x or y direction. More specifically, the partial derivative of f with respect to x gives us the slope of the tangent line to a surface in the positive x direction, and the partial derivative of f with respect to y gives us the slope of the tangent line to the surface in the positive y direction. But a directional derivative will tell us the slope of a tangent line in any direction. Let's go and take a look at this. So here we see the tangent line in the positive x direction, but if we want to find the slope of the tangent line in any other direction other than the positive y-axis, it's going to require the directional derivative as we see here. So with the directional derivative, we can find the slope of the tangent line in any direction that we want. Let's take a look at how we're going to do this. The formal definition of directional derivative involves a limit definition, just like any other derivative that we studied. But for this video, we're going to go ahead and use the working formula to determine the directional derivative. And here it is. If f is a differentiable function of x and y, then the directional derivative of f in the direction of the unit vector, which can be expressed as cosine theta I plus sine theta j, or in component form, then the directional derivative of f in the direction of u is the partial of f with respect to x times cosine theta plus the partial with respect to y times sine theta. Or we can replace cosine theta and sine theta with the x and y components of the unit vector. Yet another way to express the directional derivative would be to form a vector using the partial derivatives and then dotting it with the component form of the unit vector. Before we take a look at our examples, I want to mention one more thing. This vector here, formed by the partial derivatives, has a special name, and it's called the gradient. So the gradient of f is the vector formed where the x and y components are made up of the partial derivatives of f with respect to x and with respect to y. So now that we have this new definition for the gradient, we can now define the directional derivative of f in the direction of u as the dot product of the gradient of f and the unit vector pointing in the specified direction. So let's go ahead and take a look at our examples. Here we want to determine the directional derivative of this function at the point 3, 2, 1 in the direction of theta equals pi over 4. So we're going to find the gradient of f and then dot it with the unit vector forming the angle theta equals pi over 4. So let's first replace z with f of x, y. Now let's go ahead and determine the gradient of f. The x component consists of the partial derivative of f with respect to x. That'll give us 2x. And the y component will be the partial of f with respect to y. That'll give us negative 4y. And then the unit vector forming the angle theta equals pi over 4 is going to be cosine pi over 4, sine pi over 4. And so the directional derivative will be the dot product of these two vectors. And cosine pi over 4 is going to be square root 2 over 2, and so will sine pi over 4. This is going to give us 2x times square root 2 over 2 plus negative 4y times square root 2 over 2. Now we need to simplify this and then replace x with 3 and y with 2. Here the 2's simplify out. Here this simplifies, this changes to a 2. So we have x square root 2, and this will be plus a negative or just minus 2y square root 2. So finally, the directional derivative of f at the point 3, 2 in the direction of u is going to be 3 square root 2 minus, this will be 2 times 2, or 4 square root 2. That's going to be negative square root 2, which is approximately equal to negative 1.4. Let's take a look at this graphically. So here we see the surface in gray. This red vector here is pointing in the direction of the directional derivative, and the red line would be the tangent line at the point 3, 2, 1. And the slope of this line in the direction this red vector is pointing is approximately negative 1.4. And you can see as you move in this direction the vector points, this line is moving down, which does verify our work. Let's go and take a look at one more example. In this example, we want to determine the directional derivative of this function at the point 1, 2, 3 in the direction of the vector with components 3, 4. So this tells us that f of xy is equal to x to the third plus 1/2 y squared. Now to determine the directional derivative, we have to determine the unit vector in the direction of vector v. So we're going to have to normalize this vector. So we're going to have the square root of 3 squared plus 4 squared. That's the square root of 25. So the unit vector in the direction of v is going to have an x component of 3/5 and a y component of 4/5. Let's go ahead and determine the gradient of f. So the x component is going to be 3x squared, the partial of f with respect to x, and the y component will be the partial with respect to y. That'll give us just y. So the directional derivative is going to be equal to the gradient dotted with the unit vector. So we'll have 3x squared times 3/5 plus y times 4/5. That's going to give us 9/5 x squared and then plus 4/5 y. And now we'll sub in x equals 1 and y equals 2. So we'll have 9/5 times 1 squared plus 4/5 times 2, or 2 over 1. That's going to give us, once we have a common denominator of 5, that's going to give us 9 plus 8, or 17/5. So the slope of the tangent line in the direction of v at the point 1, 2, 3 should be positive 17/5. Let's go and take a look at that as well. Again, we have the surface in gray, and this red vector below is pointing in the direction in which we're trying to determine the derivative. And again, we said in this direction the slope would be 17/5, and you can see that if we're at this point on the surface, moving in the direction of this red vector, the line is moving up rather steeply, and the slope of this tangent line would be 17/5. That's it for this video. Thank you for watching.